Hello all, welcome to lesson 4 for Calculus AB. This video is on continuity, and in this video we're going to talk about again the three criteria that it needs for a function to be continuous at a value of c. And then once we've done that, we're going to do 4 examples where we're going to start writing out and determine if a function is continuous at a value using these 3 steps that we're going to write right here. So the first thing we're going to do is just kind of solidify again what it means to be continuous at C for calculus. So the first example that we want to talk about is that f of c has to be defined at some value, and we're going to call that value a. So over here, we're going to graph, and again, I'd like to just keep it visual. I like visual stuff. So really what this means is that f of c equals a means that the point's defined there. And that's pretty much what this means, right? So we have a point that's defined, right? It's defined at c comma a. The next thing that we need to discuss is then the limit. The limit as x approaches c of f of x. So the behavior of our function around c has to exist. And then go one step further with this, and this is the ultimate definition of this, is that then that point defined, that value, has to equal that limit. Okay, so they have to equal that limit. So then back up here in this one again, that means that limit has to equal a. And so when I graph it, it should look something like this. So I now know my function's continuous at c. Another way to think about continuity is if I were to trace along my graph, I can go through c easily without picking up my pencil or pen. So I know it's continuous. So that is the 3 criteria that we have to follow when we're proving if something's continuous or not. So I'm going to do 4 examples with you guys, and I will just say really quickly that if for some reason one of these 2 things does not occur, so let's say if the point's not defined or the limit doesn't exist, you can stop. You don't have to go through all 3 of them. If this is defined and this is defined and they're not equal, then obviously it's not continuous. So for something to be continuous, all 3 of these things have to be true. So let's look at an example, number 1 here, and this is how you're going to write this officially for calculus. Because right now we can look at a very straightforward example. So x plus 2, well, the absolute value of x plus 2. So you guys all know that the graph, the absolute value is shifting over by 2. And I also want to just say that when it's shifting over by 2, it's going to look something like this. And there's obviously a little bit more point of this, but all I care about is what's happening right here at c equals 3. So you know that this absolute value function, which is a v, is going to be continuous to all values. So we cannot, in this class, say, well, based on the graph, I know it's continuous. Nope, unfortunately, that does not work. What you have to do is you have to write everything out and show that you understand what definition of continuity actually means. So the first thing we're going to do is we're going to define the value. And this is just plugging in, right? So what is f of 3? Well, you plug in 3 plus 2, and you take the absolute value of that number, and you're going to get that that's 5. So up here in a very poorly drawn picture, you can see that it's defined at 3, 5, right? 3, 5. Now, what may help us out a little bit more with our problem is the fact that since we know what this graph looks like, and we know it's a parent function just with a transformation left 2, I can now say with full confidence that my overall function, my limit, has to also be equal to 5. Because again, I would just substitute in. This is the same thing as if I just wrote the limit as x approaches 3 of the absolute value of x plus 2. And one of the things I talked about in the last video, in lesson 3, is that substitution, direct substitution, is a totally legit thing to do. So that's how you know this limit is equal to 5 without drawing it. And then finally, we can say that the f3, where it's defined, is also equal to the limit as x approaches 3 of our function. So now I can say all this stuff is true. So now I can conclude, therefore, that f of x is continuous. It's continuous at x equals 3. Okay? And so this is the proper way of writing stuff out for calculus for us to be able to do it that way. All right, you just can't say again, I'll just look at the graph and stuff like that. So you need to figure out that the point's been defined, that the overall limit exists, and the fact that they're equal to each other. And what I've written in green, students tend to forget to do this step, right? Or they think that if the limit exists, then it's going to be continuous. But again, ladies and gentlemen, you have to remember our good old friend removable discontinuity, where there's a hole in our function, but it's not continuous. So you want to be really careful about that. So let's look at example number two. Example number two, and we're going to look at f of x is equal to this function over 20 minus 7x over x minus 3. So if I plug in 3, I'm going to get 20 minus 7 times 3, which is going to be negative 1, right? 20 minus 21, all over 0. Now, the reason why I showed this is that this right here is going to be undefined. It's undefined at x equals 3, right? Or c equals 3. If this had been 0 over 0, then we may have to look at it a little bit differently and see if there's possibly a hole that we have to take into account. Okay, it still wouldn't be continuous, so we don't really have to worry about that. But maybe we're talking about the behavior of the graph. But even though this is undefined, that means that f of c does not exist, right? It's not defined, so it is undefined. I don't know what I was going to do with that. So it's undefined. So therefore, you can now say that f of x is not continuous. And you want to make sure that when you guys write this, when it's not continuous, you want to say it's not continuous at x equals 3. You want to clarify that, because at x equals 4, this sucker is continuous. At x equals 1 it is. It's actually continuous everywhere except for x equals 3. So if this had been any other value, then you would have done the exact same steps you did over here, and it would have been continuous. So it doesn't matter that it's discontinuous at x equals 3. It's continuous everywhere else. So I could have easily changed this problem up to c equaling 5, and then again, you would have done every single step. You would have plugged in f of 5 and got a value. You would do the limit as x approaches 5 of the function, do direct substitution and get the same number, and then say that they are equal to each other. Okay, but since it's not defined, we don't have to go any further with this question. And so the answer is they want to see the work that's undefined and the fact that we have it's not continuous. And yes, you could have said that the limit didn't exist as well. But again, I like to just kind of be in the order of what we're doing. Okay, so for the next question. For this one right here, you're going to see that I want to look at c equaling 0. So this is the first time that we're going to come up with the fact that what is f of 0? So f of 0. So in this particular example, and in all piecewise examples, you have an equal to sign here. So that's what this is going to represent. So this is going to be where your point is defined. Okay, it's always where your point is defined. So in piecewise functions, your inequalities are going to be your left and right hand limits, and this equal sign is going to be where it's defined. So if I want to look at this problem, I said, okay, well, since it's equal to at e to the x, then this is going to be e to the 0 power, and this is going to be equal to 1. So I know that f of x is defined at the point 0, 1, right? So I know that that's legit, okay. And then let's change the color. Let's keep this up here. So we're going to change the color. And now I want to find the limit. Now this time, and again, you have to show work. So we've already found the right-hand limit, right? Remember, greater than is a right-handed limit. So we've already found the limit as x approaches 0 from the right of our function, and that would just be e to the x. Because again, greater than means the right-hand limit, right? Greater than is right-hand limit. And so this would just, again, be 1. So we've already found that. And then the limit as x approaches 0 from the left of our function. And remember, this is a left-hand limit, less than, and left LL. For this, we're going to plug in x squared here, and we're going to get 0. Okay, we're going to get 0. So we have to go one step further with this. We have to say that the limit as x approaches 0 from the right of f of x does not equal the limit as x approaches 0 from the left of f of x. And clearly they're not, right? 1 is 0, 1 is 0, and 1 is 1. And so you can actually conclude here that this overall limit now will not exist, right? Does not exist, because of your justification of this step right here. So finally, we can finally say after all this is said and done, that f of x is not continuous at x equals 0. Okay, and yes, I keep saying x and the problem says c. It doesn't matter what variable we're looking at. All right, so we've got one more to do here, but again, it's pretty straightforward as long as you follow the formula and find out where the point is defined. Left and right hand stuff. Students always ask, when do I know when it's a left or right hand limit? If it's a piecewise function, you need to make sure that you do it right. I just see there's an error over here, so I got to fix that for us now. Okay, so I just paused the video for a second and I fixed this where we both had less than, and that's not That's not going to work. Okay, so what I was saying is left-hand, right-hand limits. If you have an inequality, you always have to do left and right-hand limits. So let's look at example number 4. You see f of 3, and again, we're going right over here to this, right? So we're looking at this guy right here. So it's equal to, so it's going to be 5 times 3 minus 6, which is going to give us 15 minus 6, which is equal to 9. So I know that the point 3, 9 is a solution to this function. And then I want to look at now number 2, and the limit as x approaches 3. And we got to figure out what, so we've already found what the left-hand limit is, right? Because there's a less than sign here with this. So we've already found the left-hand limit. We still have to show that. And students ask, could I put an f of x here? Absolutely, you can, because we would be looking for, as we were grading these, we'd say, okay, over here for number 2, is the notation fine? Is it great? And then is the positive with 1, is the negative with 0? So we're looking for the values for these particular problems. So we've already found our left-hand limit. Well, our right-hand limit is going to be, again, where x is greater than 3, right? X is greater than 3. So we're going to plug in to x squared, and we're going to get that this is equal to 9. So we now have to say that the overall limit is equal to 9. We don't have to say that the left-hand limit and the right-hand limit are equal to each other. It's clear by them equaling to 9 here, so we can automatically jump. You can write that if you want to, absolutely, that the limit to the left is equal to the limit to the right. That's absolutely okay. It's not required here because you've already showed the work here. So the overall limit is equal to 9. And so now finally, after all that's said and done, we have to then say that f of 3 is equal to this limit as x approaches 3 of f of x, which they're both equal to 9. And so we can finally say in this problem that f of x is continuous at x equals 3. And as a matter of fact, ladies and gentlemen, this function would be continuous everywhere now as well. Okay, so it's continuous at x equals 3. But in this particular example, it's a straight line and a parabola, so it's continuous less than 3 because it's a line. It's going to be continuous greater than 3 because it's a parabola. It's a polynomial. It's always continuous. And so the only places that we really had to check for question number 4 and question number 3 are at 0 and at 3 respectively. Okay, so that's my video for just the introduction to continuity. And that's, like I said, you just have to follow these 3 steps. So when you're asked to write out or prove using the definition of continuity whether a function is continuous at a certain value, you are going to use these 3 steps. Okay, so let's go on to the next video where I will do a little bit more with this type of content.